that's the definition of that notation, but I'll just write it only once now. I hope you are fully familiar with that. So by expanding that, I managed to write least squares problem in terms of what I call the finite sum, right? So it's just going over all the rows in A. There are n rows, let's say. So that's the least squares, classical least squares problem. It assumes this finite sum form that we care about. Another random example, something called lasso. Maybe you have, if anybody of you has played with machine learning or statistics toolkits, you may have seen something called lasso. Lasso is essentially least squares, but there's another simple term at the end. That again looks like f of I. Support vector machines, once a workhorse of, and they're still a workhorse of people who work with small to medium sized data. Deep learning stuff requires huge amount of data. If you have small to medium amount of data, logistic regression, support vector machines, trees, etc., these will be your first go-to methods. They're still very widely used. These problems are again written in terms of a loss over training data. So this again has this awesome format, which I'll just now record here. I may not even need to repeat it. Sometimes I write it with a normalization. You may wonder at some point why, as that finite sum problem. And maybe the example that you wanted to see is something like that. So deep neural networks that are very popular these days, they are just yet another example of this finite sum problem. How are they an example of that? So you have n training data points. There's a